Adler32, this is just one example of a large family of hashing algorithms, but they all have certain things in common. If you look at them, what they're trying to do, what all of these algorithms are trying to do, and by the way, some of them are quite esoteric. So if you're looking to learn more about this, it's a fruitful area. There's very active research. People are designing hash functions all over the place. But in general, what they all do is they treat their input as a sequence of units. Sometimes these units are single characters, bytes. Sometimes they're 8-byte words. But in any case, you've got units, right? They all process them unit by unit, so they're all streaming algorithms. Once they see a unit, they never need to see it again. And each unit takes your hash code and flips a certain number of bits from 0 to 1 or from 1 to 0. They do the flips in many different ways. Adler does the flips based on addition and then the modulo operation, but you have other algorithms that use various logical functions or that use various shifts. In general, what they all do is they try to flip a set of numbers, and they try to flip the bits. The bits that they're flipping, ideally, they want to be scattered as widely as possible over the entire fingerprint. So Adler achieves that by the second cumulative sum, right? The sum of sums, it grows to be a very big number, so anything that you add to it has a chance of flipping lots of individual bits, and all algorithms try to replicate that in one way or another. Another thing is, when you're doing this, you have to be careful for the units not to cancel out, right? So if you have a simple flipping function, say based on an XOR, then if you see a unit and then the same unit immediately after that, that's the same thing as not having seen the unit at all, right? You're going to flip the bits from 0 to 1, and then the next unit is going to flip them back from 1 to 0. You don't want something like that happen, so you want the flips to depend on whatever was around them. And functions like sum are good for that because the bits are flipped whenever you have a carry. So they don't just look at the bit, they look at the surrounding bits as well. And there's lots of other functions that have this property. Okay, so I realize we're running late, but I want to buzz through this. When you have these methods, you are guaranteed to never have any false negatives. So false negatives would be two identical documents that end up not colliding in a hash table. This will never happen. These methods are deterministic. Once they see so if you give them the same document twice, they will generate the same hash code. It's guaranteed to go into the same bucket. So you will never ever miss a genuine duplicates with this method, but you will have false positives. You can have documents that were different that accidentally ended up flipping exactly the same set of bits. So in general, it's hard to estimate what this number is going to be, but there is an upper or there's a lower bound on it. So in the best possible case, your hash codes are almost completely random. They're deterministic, but they're scattered as randomly as possible. And in that case, if you have, say, 10 bits in your fingerprint, this means that you have 1024 possible hash codes. And each one of those hash codes is equally likely for any document. So in this case, your best possible false positive rate, the lowest possible false positive rate, is going to be just 1 over 10,024, because that is your expected rate of collision. For two different documents, think about it. You have 10 bits, you only have 1,000 buckets in your hash table. That's how many different hash codes you have. Some documents will randomly collide, and the probability of collision is just 1 over 1,024. It's a lower bound. It'll always be a little bit higher than that. It can never be lower than that. So you have a 0 false negative rate, slightly positive false positive rate.